Welcome back to our Flownex online training sessions. This is our 8th training session, and today it is time for our heat exchangers. So let's turn on the heat and dive right in. Earlier in the course, we modeled just one side of the heat exchanger using a flow restriction with specified heat load. But where information on the heat exchangers and both fluids are known, you can do a much better job with our proper heat exchanger components. The various options available are the finned tube, general, recuperator, and shell and tube heat exchangers. Each has their own specific inputs and appropriate calculation methods to get you straight to the best results. You'll also notice that there is a primary and secondary component allocated to each. You need to drag in both and assign the different fluids working on each side. Just make sure that they are thoroughly connected by the indicated solid connection line. On the finned tube primary side, in this case our fin side, the component requires characteristic charts for its heat transfer and pressure flow characteristics as given by Case and London, as well as specification of the predominant flow direction, heat transfer area and area ratio, flow path distance, and the free flow to total fluid area ratios. Obviously, we'd like to specify our tube wall material, and for this you can give either the material conductivity and heat capacity, or select from our database the type of metal and specify its wall thickness and total mass. On the secondary side, we need to specify the tube side layout and its geometry. And remember that you can press F1 to get more detailed information on the input specification and underlying theoretical principles on any component. The recuperator is my favorite when it comes to detailed heat exchanger modeling. For all weird and intricate kind of tube layouts, like a shell and coil or printed circuit heat exchanger, this one has similar inputs to the fin tube one. But here I have the option not to specify a chart, but rather conveniently adapt the pressure loss and heat transfer correlations obtained from the design specification or literature. The recuperator component furthermore assumes equal flow path distances for both hot and cold sides. So the secondary side's inputs boils down to only correlation factors and flow area specification. Extremely effective and easy to use, I'd say. The shell and tube component is in my mind one of the most complicated components to use, and should only be attempted for very detailed designs according to its specific function explained in the help manual. For general systems modeling, however, I would much rather recommend the general heat exchanger primary and secondary components. For a shell and tube heat exchanger on system level, you can click on Data Specification and then U-tube. Inputs are simply the AU value, number of shell passes, and then pressure flow specification, similar to the general empirical resistance component for both primary and secondary sides. Other selectable types are the crossflow, counterflow, and parallel flow configurations, each requiring only the AU value and pressure drop specification, and then also the effectiveness method specification. But let's pause here for a bit. Can you even remember what is this AU and effectiveness gibberish I'm talking about? Let's quickly run through the theory. First of all, for a fully insulated heat exchanger, the hot side's heat loss, mCp delta T, is always equal to the hot side convection heat transfer, which is equal to the tube wall conduction heat transfer, which in turn is also equal to the cold side convection heat transfer, which is finally equal to the cold side heat take-up. This conservation of energy principle is fundamental to all such cases. So in terms of heat transfer resistances, we have the convection resistance, some tube fouling, conduction resistance, again fouling resistance on the other side, and another convection resistance. And these resistances can all be grouped together to form the overall heat transfer coefficient termed AU, from which heat transfer can be calculated by AU times the log mean temperature difference applicable to counterflow or parallel flow. Are you following? The effectiveness of that heat exchanger is the ratio of actual achieved heat transfer to maximum theoretical heat transfer. So effectiveness equals mCp delta T of either the hot or cold side divided by the minimum of the MCPs of the two sides with the maximum obtainable temperature difference. I bet you still vaguely remember these principles at the back of your head. For more local related heat transfer, we also have the heat transfer components, which include detailed specification for conduction, convection, and even radiation. They require more inputs than the integrated heat exchanger components, but are more flexible in its use for detailed heat transfer modeling and become very powerful once you get accustomed to the use. But we'll take them on a little bit later. So let's quickly go back to our Flownex exercise and say we want to replace our heat exchanger with a shell and tube configuration with overall heat exchanger AU of 2.4 and 2 passes. We are still looking for 100 kilowatts overall performance and 70 kPa pressure drop on the water side. For the hot side, we have hydrogen coming in at 80 degrees C and 1000 kPa. With a pressure loss over the heat exchanger of roughly 10 kPa. So on the Flownex network, we can drag in our primary side and give the AU and shell pass information. The pressure flow correlation remains the same, so I can copy my CK value for the water side with 1 and 2 as general values. For the secondary side, I need to assign gases hydrogen. Add my inlet boundary value and its values. Together with an outlet mass source specification to get my system going. And with that, I can estimate my CK value to be around 200,000. 1 and 2. Solve. Drag in the results for pressure loss and heat load. And let's try again manually a mass source of 0.15 to get closer to 100 kilowatts. And then finally set up a designer to get to an exact heat load of 100. There we go. The last bit of getting the secondary side to exactly 10 kPa, I'll leave up to you. Important to note is that the direction of the arrows doesn't determine the heat exchanger's flow convention, since I specify whether it performs as parallel or counterflow. So I can draw them any direction I'd like to simplify my network layout on the canvas. And that's it for today. In our next session, we'll look at the different containers in Flownex and add one to our network. But until then, have a wonderful time.